we look into quality and testing. This is lecture number 5, which basically tells us the first thing is that there are different disciplines in software engineering. So the lecture quality assurance and testing, inside this discipline map we have development. First of all, this is the first discipline in software engineering. Requirements, context analysis, requirements engineering, design, architecture, detailed design, implementation is part of development. And we have quality management. This is the second one. We have quality assurance and testing, test inspection, metrics, processes and process models, improvement, process models, maturity levels. Then we have evolution, where we roll out, operation, maintenance. We have further development, and then we reuse, re-engineering. This is evolution. Then we have management, for example, change management, strategy, economy, team, dates and risks and customers, etc. Right now we are in the quality management sector, which is the second one. We will be doing this. Our motivation for the basic topics that are across all are the configuration management, documentation, knowledge management, and people in software engineering process, and digital ethics and tools. Now we have motivation and challenges. Why quality is hard? Software quality problems from everyday life, like BAFOG delay, software didn't recognize new rates, Deutsche Bank terminal failures, for example, GM recall of 4.3 million cars. So Roch AccuCheck Connect diabetes management app, for example. So why are there errors? So first we discussed software quality problems from everyday. These are like everyday problems like BAFOG delay, software didn't recognize new rates, Deutsche Bank terminal failures, and GM recall of 4.3 million cars, and Roche AccuCheck Connect diabetes management app. These are like everyday software quality problems. Why are there errors? The primary cause of an error is an incorrect implementation. The real causes are manifold. So notorious example, we have Ariane 501. Ariane 5 succeeded the Ariane 4 family 100 plus successful launches with lots of reuse code. Maiden flight 4.6 1996. After a few seconds, the rocket blew itself up. Mission was lost. Cost was more than 500 million euro. Program held up 3 years. The primary cause was that operand error during conversion. So we had operand error during conversion, lack of exception handling basically. So this is like lack of exception handling, like negative taste casting, let's say. Root causes are value ranges were assumed for the variable concerned but not documented. Distributed responsibility with lack of documentation. These were primary causes. That operand error during conversion, lack of exception handling. But the root causes were value ranges were assumed from variable concerned but not documented. Distributed responsibility and lack of documentation. So the assumptions could be not verified on the basis of planned trajectory, as this was not part of the requirement specification, management, and lack of software engineering. These are the things that happens, right? These are the assumptions that could not be verified on the basis of that planned trajectory. It's not the part of the requirements specification, for example, management or lack of software engineering. The quality assurance measures that could have prevented it. Now, cost management can happen. Reusing existing software must not be reused without inspection. So you must inspect it before reusing it again. And we have specification, for example, system tests under the most realistic possible conditions. Like you realistically test it. Then you review it with you do inspections. Like there are quality assurance measures that could have prevented this. And what are these measures? These are cost management, for example. Reusing existing software must not be reused without inspection. Like the cost management needs to be done in a way that you inspect the software first. Then you do specification, like system tests. Specification is like doing system tests under realistic conditions. What if we're really going to run it? How it's going to be like? And then reviewing it, inspectioning by competent experts. Like let the experts review this. How do you ensure quality? So there are 2 ways to ensure quality. The first is quality management, which is an established process for dealing with quality, like describe quality, requirements engineering, evaluate quality, software SW testing, achieve quality, entire lectures plus the software SW architecture, then find errors, defects, SW test, avoid errors. We go ahead and we achieve quality by entire lecture we have on it, and software architecture we are finding errors and defects. This is SW testing. Then we avoid errors, defects, Then we do quality assurance, concrete procedures. We have constructive quality assurance, analytical quality assurance, and organizational quality assurance. These are different types of quality assurances that we have. And then this was the first one, was quality management. Then we have that quality cannot be tested in the product. We cannot test it in the product itself. Organizational and constructive measures are more important and are supplemented by analytical measures. So you cannot test it the product in the product. So organizational and constructive measures are more important and are supplemented by analytical measures. So you need to do analytical measures for that. For example, software quality assurance map. What we have in this quality assurance map is that first thing is organizational, software project management. Second thing is constructive software engineering. The third thing is analytical, software examination. For example, conducting reviews, doing static test, doing dynamic test. Now we know what is what. Reviews are analysis by humans analyzing. These are reviews. Static tests is again analysis. It's still not execution. For example, you just look at the code and you check for spellings and st-lints, for example. Just looking at the spellings and not really executing the code yet, not really putting the run in the compiler. Once you put the run, that's the dynamic text when you're executing it. So then we have software test objectives and terms. Why do you test? The primary objective of testing is to find errors. There are many other objectives as well. Further objectives are, for example, verification. Have all requirements been met? To create trust. This is a second objective. Confidence in the level of quality. Information, for example, for stakeholders. And being able to assess quality risks if there are any quality risks involved. Basically proceed further and we look at different kind of terms that we have. Why do we test? The primary objective of testing is to find errors. There are many other objectives, just like we already discussed. Then we have different definitions. We have testing is the process within the software development lifecycle that evaluates the quality of a component or system and related work products. For example, these are testing. It's the process of lifecycle that evaluates the quality of a component. Then we have failure, an event in which a component or system does not meet its requirement within a specific limit. For example, a user may be able to click 3 times less than 2 seconds. This is a requirement and this is failure. It's also a bug. Then this failure can lead to a defect, an implementation in a work product where it does not meet its requirement and becomes a cause of failure. A good example would be something I could be able to show is something like this. For example, a developer adds a bug, a defect to a banking app, which then leads the user open app. It instantly crashes. It's a failure. It's a complete failure and user notices it. So a bug could be something that I know it's just part of the code a little bit, and I'm not really sure if it's really gonna crash the whole app, because the moment the customer or the user notices it, it becomes a failure. So it's just a bug. It's just a defect. But then defect leads to a failure in some cases because I didn't fix the bug. It just led to a failure. The whole website didn't work when he wanted to access it because of a small bug. Then we have a failure, means a power grid goes offline. It's a failure already during a storm. And then suddenly a shutdown corrupts the defect, which causes a defect, like the hardware of a connected computer is having a problem because of it. So this is also possible. Then error is a human action that leads to an error. So this is the error chain. Error leads to a defect. Defect leads to a failure. When a customer reports error, it is a failure, just like I said. A visible occurrence of a fault. So this is a chain. And of course, defect can lead to failure and failure can lead to defect. That's also possible. Then we have test case designs. A test case contains name, test objective, what needs to be tested, tested request, reference to a request or an error. Precondition, what state is it in right now, present. Post condition, what data state after execution, and then description of the test steps, like input, expected input, like for example, description of test input, expected output, expected expectations, test infrastructure, what it needs to execute on it, all of these things. Then we have example. For example, there's a requirement, then we name it. The test objective is that I need to insert an item in an array to-do list. Then the precondition would be that the to-do list is right now empty before I add it. The post condition should be that to-do list contains added elements. This is the post condition. Then we have logical versus concrete test cases. Logical test case is the value range. For example, empty list, one element, many elements. There is no specific thing like exact number. Specific concrete test case is concrete input. Example, 5 times in less than 2 seconds. This is a concrete test case that gives us exact things to play with, not just say, oh, many times. Then we have positive and negative test cases. For example, positive is that corrected input gives us expected correct result, while negative input, for example, negative test cases are like trying to do exception handling, inadmissible entries, or expects exceptional treatment. For example, the main requirement positive test case is that it needs to open, it needs to do what it's supposed to be doing, and it does it. That's it, passed. Then there's a negative test case. For example, out of nowhere, I decide to open the app, close the app, open the app, close the app 5-10 times. It is not what I'm supposed to do. It's not positive test testing. It was never part of the requirement, but it still leads to the app being crashed. So this is exception handling. What if I enter random values in the array, in the input when I want to enter something? These are negative test testings. Then we have who tests and psychology of testing. Basically, everybody tests. Everyone is responsible for quality of a product, but quality cannot be tested into a product. So the psychology of testing is that the task is that skyscraper, cathedral, temple prayer versus cathedral, player, temple, skyscraper. It is read from left and a hypothesis is generated. So the last word is usually picked. So this is generally picked and this is generally picked. Test success is influenced by psychological factors. For example, blindness to your own mistakes, difficulty in leaving the path already taken, like for example, human weakness, and then in the interpretation of information. Then we have techniques to minimize your own bias. For example, doing like you might have a bias that, oh, everything I'm doing is right. For example, pair programming. Someone is looking at what you're doing, is testing while you're working. Then we have test-driven development. First test, then code, then write the code. Then we have test review by another person. Now we know when and how to test. When do you test? You always do it as early as possible. We are continuous testing because untested code is not code. The earlier a defect is found, the cheaper it is to fix. Now, how do others test? Fuel tank, for example, scanner checks completeness, correctness of installed parts. Crash test. Different types like scanner to scan completeness and correctness. Crash test to withstand certain impact forces. Temperature tests, functional down up to minus 40 degrees. Only if the tank passes the test, it will be delivered. So after passing all of these tests, then we have test levels and objectives. We have unit tests, component tests, uncover errors in components. Then like unitly testing on individual level. Then we have integration tests, integrating all of these together, uncovers in integration multiple components together. System tests, uncover, these are different test levels, for example, uncovers errors in end-to-end application workflow, like the whole system itself. Then we have acceptance tests, generate confidence in product, check availability, applicability for intended use. So is it applicable for the intended use now? Now we need to know, how do you test? We test systematically based on experience, never without a goal, always with a goal and always with a plan. Different methods we have: black box testing, white box testing, equivalence scale analysis. This is something that we will study next semester, but for now, black box and white box. Now, black box is derived without knowledge of a program logic. Input, actual result. So we don't know what's happening. It's a box. We shake the box to test it. We don't know what's inside of it, but we can still test and see how it sounds, what it's inside of it, how heavy it is, and things like that. Then we have white box testing. We have derived knowledge of it. We have input leads to internal node analysis, and then we have result. Now we have how much testing. Software can be delivered with acceptable risks. How much we test actually depends on what criteria we have. Why are we making this software for? Are we making it for a certain hospital? Then it cannot have a downtime. So we need to do a lot of testing in certain areas, and it can be delivered with certain acceptable risks. This risk is acceptable, or certain risk is not acceptable. So a risk that a service is down for 10 seconds is not acceptable for emergency hotline. Then we had that needs to a lot of testing. So how much testing is based on that? Then we have test documentation. We have test specification. Specifies the test results. Logical test steps are supplemented by specific test data and steps before, during execution, for example. We have specific data often only logged on error. We have error logging. Error log contains, this is the test documentation. We have error log contains the reference to the test case that led to the error. Then all information required to produce it. In particular, the case test data, for example, classification of the error. We have Spillner and Linz. Then we have error severity. According to Spillner and Linz, it says class 1 is a system crash, complete with potential data lost, the entire system crashed. Test object cannot be put into use anymore. Then we have class 2, which is crucial function exhibits error, requirements not considered or implemented wrong, or are implemented wrong. Then we have test objectives can only be used with significant restrictions. Then we have class 3, functional deviation, normal error, for example, not that much is a normal error. Requirement was wrong or only implemented partially, not implemented fully. Test object can be used with restrictions. So we can still use the thing, but with restrictions. But in 2, the crucial function exhibit errors. The most important ones, they make errors, and then requirements are not considered or implemented, or are completely implemented wrong. Test object can only be used with significant restrictions. So we have significant restrictions here. Here we have some restrictions. Here we have many restrictions. Here we have some restrictions. And class 4, small deviation tests can be used without restrictions. So we have some deviations, but it can be used without any restriction. Then we have 5, that cosmetic error, like a logo is not on the right place. These are like test object can be used without restriction still, but we have cosmetic variant here. We have test protocol. According to Spillner-Linz, summary of executed test cases, what was tested and result. What is the result? Typically tabular plus the natural language at system test level. It is the basis for discussion with the customer in preparation for acceptance. Then we have validation versus verification. Verification versus verification. Verification is testing against requirements. Are they fulfilled? Question mark. Validation, check against the application context. Is it useful? Can we use it? Is it usable? So fulfilled is based on requirements. Verification is against requirements. Validation is against, is it even usable? So usable, fulfilled requirements. Then we have container example. Container can be filled with water, has a handle, made of plastic, blue, capacity 10 liter. Verification asks, requirements fulfilled. Validation asks, is it useful? Can you use it? So verification via usability, validation via usability. Not everything that is functionally okay is also easy to use. So it could be functioning okay, but it's not even usable. You cannot use it. It's functionable, but it's very hard to use. And that's more about validation, that it's really hard to use it. So it's not usable. It's hard to use, or it cannot be used at all. Then we have Jacobs Nelson 10 hierarchies for design of user interface, UI design. Principle number 1 is visibility of system status, feedback. Keep user informed of the current status with timely feedback. For example, game sound during collection, haptic feedback, animation after a visible action, visual feedback when a level is completed. So these are visibility of feedback to the user. Then we have principle number 2, correspondence between system and real world metaphor. Speak the user language. Follow real world conversation. Game backpack is full. Go to trash can versus rather than just a synaptic error code. So we need to tell him that, okay, it's filled. Now go this, do this, the next steps. We talk to the user. Then we have principle 3, user control and freedom. Navigation, for example. A clearly marked, so we have feedback, we have metaphor, we have navigation. A clearly marked emergency, exit, undo or redo. game undo steps, pause game, change character, control options, abort, exit. So these are navigation related things. You can navigate. This is freedom. We have consistency and standard, which is consistency. For example, follow the conventions of the platform game. Platform button, labels, colors, controls, position uniformly, consistent shortcuts. Do this to go right. Not that, oh, for some time it works to go right, but then it doesn't anymore. So it always does the same thing. You, if always press the arrow up, then it always go straight. This is consistency. Then we have error prevention, preventing the error. Careful design that prevents problems. We offers a confirmation option. For example, in game, we have placement only in permitted locations. It locks levels not yet unlocked. So we have careful design that prevents problems. Only permitted locations. You cannot just go wherever you want in the game. You can only stay in the game. Then you have lock levels not unlocked yet. So what's not, we have preventions. You cannot just do whatever. There are limitations so that the game does not have illogical situation. Then we have memory, which is recognize instead of remember. Make objects, actions, and options available to cut memory load. So we have game display the input to trigger an action. So it displays input so we can trigger an action, show how many levels completed, and how many levels you did. 5 levels you already did. So you have memory. It tells the user, it talks to the user in UI that you know you did 5 levels. Then we have flexibility, efficiency, accelerator for experienced user. So we have flexibility and efficiency of use. This is efficiency, for example, game shortcuts for frequent functions. These are several navigation options or arrows and keys and extra things. If you get proficient with the game, you will be able to use it much better. Then we have aesthetics and minimal design, for example. No irrelevant info. Observe contrast, repetition, alignment, and proximity. Now for game, consistent visual indicators, group related buttons, common color codes, red for demolition and maintaining style. So it is a certain kind of design code. It's not that everything is random. We have color codes, we have contrast, we have alignment, and all of this is design. And principle 9 says recovery. Support user in detecting, diagnosing, and correcting their faults. For example, a simple language message state the problem, suggest a solution. Simple language, we have a simple language messages, then we have it states the problem, then we suggest a solution. For example, game, if a character gets stuck at a corner, it tells the user that press X to get out, instead of saying error code or message. Both best. For example, the best thing would be that saying this is not right, go to press X, get out. Press X to get out. This helps the user, so it's a recovery. It's not that you're stuck somewhere forever. Then you have principle 10. It helps us document help, for example. It's easy to find, task focused, specific steps, not too extensive. For example, game self-explanatory, community tutorials, for example. We have help and documentation, community tutorials, self-explanatory guides, easy to find, task focused, specific task, not too extensive. Then we move on to the new topic, that is reviews. The definition is that a type of static testing, this is again static testing because you're not really executing anything, in which the quality of a work, product, or process is evaluated by real individuals. When is a review useful? It's always useful before milestone, before customer appointments, before handovers to the next phase, before you accept in any result. Who carries out reviews? Everyone carries them. Everyone is responsible for the quality of a product. How do you carry out reviews? You carry them systematically. Check. Now, we have different ways to carry out reviews or extract requirements. We do it checklist based. A checklist in advance is used as a basis. We have role based review. We can extract reviews based on this. And we can extract reviews based on roles, review from a specific perspective, customer perspective, asking only from a customer review. So user might say something different and a developer might say something different. So we do role-based review systematically. Then we have perspective-based. Certain aspects define in advance: consistency or compliance. So we define certain aspects that we want to review in advance. Also ad hoc, formal versus informal. A combination of both is effective. So we do formal and then we do informal reviewing. Reviewing documentation, we have checklist for checklist perspective-based reviews. We have processes description for formal review types. Then we have review protocol, which contains all findings plus a summarized evaluation. Then we have rules for formulating review findings. To formulate neutrally and objectively, we classify errors by severity. A review refers to an artifact and not to a person. Provide an opportunity for queries. Then we have rule of 10, defect cost over the life cycle. Error occurrence versus detection. The majority of error are caused during the development, but are often noticed very, very late, during testing or even during use. So the rule of 10 is that the cost of rectifying faults increased by a factor of 10 from one development stage to the next. Across the life cycle, a single fix rises. For example, €5 if you find it now. If you pass it to the next stage, then if it found then it's €50 cost. If you find it much later, then it's €500 in cost. So if you find it as early as is possible and you fix it, the fault, then the defect, then it's perfect. But if the user finds it, then it's the worst because it's the last stage and it's the most expensive then. The extreme cases recall us that the cost can reach up to 1,000 times the manufacturing cost. Current automated recall campaigns can add up to €1.4 billion. Then we have literature, and that was it for the lecture.